Thank you very, very much for your introduction, also for your kind invitation to speak today, and also for helping with translation. What I want to do in this talk is three things. First, I'm going to outline the steps in going from the physics of the 1920s to the chemistry of the 21st century. I'm going to do this in an extremely non-mathematical way, and a theoretician would throw me out, but my purpose is not to show you the beautiful mathematics that connects the Schrödinger equation to what we actually do, but rather to convince you that what we do is not magic. It has a logical basis, and it's actually rather simple conceptually. The second thing I want to do is introduce a small number of methods, schemes, recipes that actually can be used to deal with problems of relevance. And finally, I want to just give a few examples, nothing really specific, of types of problems that you can deal with. So I'm going to keep this in a very, very general sense. But this is an important slide. What is theory? What is experiment? Theory is a set of rules. We may not know what they are, but once we find those rules, we can test those rules by experiment, because experiment is really the consequences of a set of underlying principles. What this means is that we should be able to calculate, if we know those principles, we should be able to calculate what an experiment gives us. Okay? You can use the word modeling, you could use the word simulation, but essentially it's applying what we think are the underlying rules to areas or properties that we think are important. Okay? In the case of molecules, it all traces back to 1927, the Schrödinger equation. This is an equation which looks extremely simple. I've taught physical chemistry many, many times, and the first thing you tell people is you can't cancel psi. It's not an algebraic equation. It's called an eigenvalue equation. It's a differential equation. Okay? The most interesting thing about it is that it is not actually an equality. It's a probabilistic equation. It tells us something about probabilities, how likely something is to occur. Okay, the Schrödinger equation has been solved for the hydrogen atom. I realize I'm walking in front of the screen. It has been solved for the hydrogen atom. It's never been solved for anything else. It's never been solved for the helium atom. Pretty simple. So what do we do? Well, if we're interested in hydrogen, we're fine. If we're interested in helium or anything else, we have to make some approximations. And in fact, there are only three approximations. The first one is very simple, and we're going to forget about it immediately. We're going to use it and forget. It's called the Born-Oppenheimer approximation. It says the following. Molecules are made up of two kinds of particles. They're made up of nuclei, which are big and move at the speed of sound, maybe, and electrons, which are much smaller and move at the speed of light. From the point of view of an electron, the nuclei aren't moving. So we're going to assume that nuclei don't move. What that allows us to do is to solve for the simplest molecule, H2+. Only one particle, the electron. The nuclei are fixed. Okay? Not very interesting. The second approximation is the important one. It is that we force electrons to move independently. we know that this will provide an equation we can solve, because if electrons are independent, then in fact we're dealing with a set of one-electron equations. We know how to solve a one-electron equation, the hydrogen atom. Mathematically, what we're doing is we're separating variables. We're forcing a solution in terms of a product. Not quite, but I don't want to go any further than that. So that's the second approximation. That's called the Hartree-Fock approximation. It was done in the 1930s. The third approximation was the last of the three. It's the most chemical of the three. It says that molecules are made of atoms. We know that. So the solutions of molecules should be made of the solutions of atoms. It's reasonable. We don't know the solutions of atoms, but we know the solution of hydrogen atom. And so now we're going to force the solutions of molecules to be written in terms of combinations of solutions of hydrogen atom-like solutions. Pretty simple. What we've done here is we've reduced a differential equation into a problem in linear algebra, a very complicated problem. Now, this was probably done in the 1930s, but it wasn't really put together and published until about 1951, a long, long time ago for most of you here. The reason for that was that technology wasn't really there. The result of doing all this is to produce a theory or a method which has an enormous amount of arithmetic required. And it was not possible to consider, how do I do 1 billion or more arithmetic operations with a pencil or a hand calculator. It just didn't exist. And it took the invention of the digital computer, which is the late 1940s, to actually make this a reality. Okay, now what I've been talking about can be put in terms of a diagram. I'm going to put my two approximations. The first one I'm going to forget about. It's so good we can forget about it. I'm going to put them in a diagram. On one axis of the diagram is the dependence of electrons. Down here, we're independent. Here, we're dependent. So there's a range of things we can do. Here is the set of atomic solutions. We can have the smallest possible set and an infinite or complete set. Okay? So this diagram defines a model. And any point on this diagram is, if it's a well-defined point, is a different recipe. So pretty simple. Now, there are two limits to this diagram. There's a limit down here. This is the smallest possible set of atomic functions and completely independent. That's a limit. It turns out that limit isn't very good, but it's something that actually is rather simple. Up here, somewhere, there's another limit. Completely dependent and a complete or infinite set of functions. That's another limit. This limit is good. This is exact. It's also impossible. So what counts is the place between these two limits. Any point between those two limits is going to be called a theoretical model. There are many of them. Those models have to have some well-defined criteria. There are three important ones. The first one is it has to be well-defined. I have to be able to transmit to you what the method is, and you have to be able to reproduce it, like anything in science. Secondly, it has to be unbiased as much as possible. You can't put the answer in. Okay, there are a lot of theories, a lot of methodologies in chemistry where we, in fact, fit data, and we use so little data that you can't help but getting it right. Now, you can draw a line between two straight points. You can draw a straight line between 2 points. The third one, and probably the most important, is it has to be applicable. If I give you a theory that you can apply to something so small that you don't care, what good is it? So those are the three important points. Now, one would like to believe that if I do this and if I push these to the top limit, that what I'm going to get is experiment. And that's not quite true. And let me try to show you why it's not quite true. Theoretical things differ from experiment for a number of reasons. The first thing is that we're talking about molecules that are isolated. So we're talking about an experimental condition that is the dilute gas in the extreme. Now, there are some experiments that are dilute gas. Mass spectrometry is such an experiment. But most experiments are carried out in solutions or in liquids. Let me give you an example of what I mean by this, and I'll draw one from infrared spectroscopy. It's a clear one. I've given two infrared spectra on this slide. The one that looks like an infrared spectrum to you is in black. The other one that doesn't look at all like an infrared spectrum, in fact it looks like an inverted mass spectrum, is the calculation. What's happening? Well, there are two things happening, but let's go one at a time. The first thing that's happening is that I have sharp lines. If you actually perform an infrared spectrum measurement under dilute conditions in an argon matrix, that's exactly what you see. The broadening is due to collisions with the media or with other molecules, and it's referred to as rotational broadening, but it's due to collisions. So we don't have that in the calculation. What I'm calculating is a frequency and an intensity. So how do I broaden? Well, it's pretty simple, actually. What I do is I fit the data to a very simple function which has a width. The one that's commonly used is called a Lorentzian function. It's not important. It has a width. And I treat the width as a parameter. Very, very generally, that parameter could be called temperature. But I don't even care. So here we now see something that begins to resemble. You can see that they sort of look the same. They're different, but they look the same. Okay, let's go a little further now. The theory differs from experiment also because we may be describing something simpler. In the case of, I'll use infrared again, in the case of infrared spectroscopy, what we're describing, this is the plot I just showed you, is a frequency that's been calculated to assume that the potential, the frequency is the curvature of the potential. It's how steep or how shallow I am. The practical calculations assume that the potential is a quadratic function. Quadratic function goes to infinity. It's too steep. The real function goes to this. And so what we want to do is recognize there's a systematic problem where too steep, frequency is too large. We're going to put another parameter in here. It's called the scale. And we're simply going to scale that by some number. It's very close to 1. And when you do that, what you see is now, gee, they really do look pretty similar. Now, they're still different because there are things in the experiment that we're not accounting for. We're not accounting for rotational fine structure. We're not accounting for the word slips my mind, the doubling of frequencies, overtones. Okay, there are a lot of things we're not accounting for. But again, you can see what's happening. Okay, there's a third reason. When we do an experiment, we like to believe that we're putting in a pure compound. One compound. I mean a lot of one compound, but one compound. What if we're not? What if we're putting in a mixture? Or what if we're putting in a compound that will be a mixture, like a tautomer or even a conformational change? I'll give you one very simple example of that. This is the black line is the experimental infrared spectrum of this 2-hydroxypyridine compound. The red line is the calculated spectrum. They're almost perfect, with one exception, and one should never ignore the exceptions. Never ignore the exceptions. There's a big line there. That line is due to a tautomer. If you take the infrared spectrum of tautomer, this is the calculated one. I should put up the experimental one. It looks the same. It's pretty bland, except for a big line. It's carbonyl stretch. And if you add these two together, and I don't know what ratio to add them together, but if you add them together, you get the whole thing. So there's a simple idea. How do you choose a model? I'm going to suggest that there are many recipes, very large numbers, terrible. How do you choose it? Well, one way, which was the common way for the first 20 years, is that you kept changing the model until it agreed with you. That's foolish for a number of reasons. It's foolish because all you're doing is showing that quantum mechanics works, which it does. And you're really not putting theory in a very good position. You're really putting it in, just rub my back, convince me that everything is well. That's not the way you should put theory. The second problem with that method is that you're not taking advantage of experience. If you gain a lot of experience with a few methods, you'll know exactly how they behave. And when you give them into a new situation, you'll know exactly what the error limits should be, what is really correct and what is incorrect. So I'm going to go in a different posture. And I think a better approach is to pick one method or two methods or five, I don't care, and to gain experience with them. Now, you don't have to gain the experience, because if those methods have been chosen and there is experience with them, then you can just use that. Exactly the same as when you do an experimental measurement. There are precision problems in all experiments. And if you know them, because other people have done the work, then you know what to expect of the experiment. You know how accurately you can measure a melting point or what have you. Okay? This is a philosophy I took out of my PhD mentor, John Popel, and his philosophy was keep it simple. Instead of starting from the very top, the most expensive thing you could do, start from the bottom and work upward. And when you finally get to something that looks acceptable, realizing that experiments also have errors, then you stop. At the moment, and this is one of the few slides I'll put in nomenclature. I took out a couple slides. They're in the internet. They're on the presentation, the internet, to define these words. But at the moment, the independent theory, the bottom left corner, is called so-called Hartree-Fock theory. If you move up, you can move up diagonally to a very well-defined theory that is quite good and quite costly. And in the last couple of decades, we've learned how to keep the good and get rid of the costly. And their theories are called density functional theory. I'm going to be talking about the results from density functional theory. I don't want to get into details at this stage.